Hi everyone, I'm Przemek Mroz. Currently, I'm a postdoctoral researcher at Caltech. I'm working in the time domain astronomy group, mostly on gravitational microlensing. And today I'd like to tell you what we can learn about our own Milky Way by studying gravitational microlensing events. Because microlensing is a very unique technique that allows you to detect objects that are extremely difficult to find otherwise. Objects such as isolated black holes or called exoplanets. I think that some of you may be familiar with this image, which shows a gravitational lensing by a cluster of galaxies. So gravitational lensing is a direct consequence of the Einstein's theory of general relativity. Basically, general relativity tells us that massive objects, such as clusters of galaxies, can warp the fabric of spacetime around them. And so the light that is traveling near such a cluster is bent, its trajectory is curved. And so images of objects located behind the cluster will be distorted. For example, here, the background galaxy has a shape of arcs and rings around the galaxy cluster. Gravitational microlensing is basically the same phenomenon, but it occurs on much smaller scales within our galaxy. So during gravitational microlensing events, the light from a distant star, known as a source, is bent and magnified in the gravitational field of an intervening lensing object. And because the source, the lens, and the observer are moving relative to each other, we can detect a transient brightening of an otherwise constant source star. And we call these brightenings gravitational microlensing events. What is important is that microlensing allows us to detect objects that are dark, that do not emit any light, objects such as black holes or planets. And by studying the shape of the light curve, by modeling the shape of the light curve, we can infer the physical parameters of the lens. So we can estimate its mass and its distance from the observer. For example, the duration of microlensing events, quantified by the Einstein timescale, is correlated with the mass of the lens. So basically, the lower the mass of the lens, the shorter the event. And so typical microlensing events by Earth mass objects have timescales of just a couple of hours. Microlensing events by stars have timescales of several days, typically 20-30 days. And we expect that microlensing events by black holes are very long. They have timescales. They should have timescales on the order of 100 days and longer. So by modeling the shape of the light curve, we can get some physical parameters describing the lensing system. And this animation shows basically what happens during the lensing event. In the center of the upper plot is located, the lens is located in the center of the upper plot. It is marked with this orange asterisk. And the source star is marked here with a red cycle that is moving near the lens. So the image of the source star is distorted. Actually, two images are formed, and these images are shown in the blue color. Two images are formed, And because the angular separation is usually too small to be resolved with the current telescopes, we can only measure the combined brightness. And it turns out that during the lensing event, the combined brightness of the two images that are formed may be up to a factor of 100 times larger, higher than the brightness of the unlensed source. So these events can have very high, very large amplitudes. Microlensing occurs when three objects, the lens, the source, and the observer, are almost exactly in one line. So as you can imagine, the probability of such a chance alignment is very small. And this is why, for example, if we observed only one star located somewhere in the galactic center, we would need to wait about 1 million years to see that star being microlensed by some foreground object. And this is why, of course, we cannot afford to do that. So this is why modern microlensing surveys, modern experiments that are searching for these events in the Milky Way, they are observing hundreds of millions of stars toward the galactic center, where the density of stars is largest, and so the chances of microlensing are highest. Currently, there are three major microlensing surveys. These are OGLE, MOA, and KMT-NAT. And these experiments are dedicated to observing the galactic center and searching for gravitational microlensing events. So basically, they are finding about 2,000, 3,000 microlensing events every year. And these surveys have already produced a number of scientific results. I don't have time to discuss all of them. I will just highlight a few. For example, microlensing is a very good method to detect low mass, widely orbiting cold exoplanets that are almost impossible to detect otherwise. So the image on the left shows the distribution of the distribution of masses and semi-major axes of known exoplanets, and the colors code the detection method. So as you can see, like most of transits are most of nearby closely orbiting planets have been found by transits. Radio velocities and direct imaging allows you to detect large, giant, Jupiter-sized planets, whereas microlensing, here shown in blue, is capable of detecting very low mass planets, Earth mass planets, at relatively large separations between 1 and 10 astronomical units. So such planets cannot be detected otherwise. I think so far over 100 exoplanets were detected with microlensing, and here is some example. So we have this symmetric microlensing light curve by this host star and a short duration anomaly on top of it. So the anomaly in this case is caused by a very low mass planet. Microlensing allows you also to detect very exotic objects, such as free-floating planets, which are basically planets without a host star. Our current understanding of planet formation tells us that there should exist a population of objects that have been ejected from their parent planetary systems, and they are now free-floating. They are now wandering the Milky Way without a star. So how to find them? The plot on the left shows the distribution of timescales of gravitational microlensing events detected toward the galactic center. And as you can see, there's an excess of very short duration microlensing events with timescales shorter than one day, and as I said at the beginning of my talk, the shorter the timescale, the lower the mass of the lens. So we believe that excess of short duration microlensing events is caused by a population of low mass free floating planets that are about as common as stars in our Milky Way. And the plots on the right show just two example light curves of short duration microlensing events by these objects. On the other side of the mass spectrum, microlensing allows us also to detect isolated stellar remnants, that is, neutron stars and black holes. And because they have relatively large masses, we expect that microlensing events by these kinds of objects should have relatively long timescales, on the order of about a year. And we can also search for such long timescale microlensing events in our event samples, and then estimate the masses of the lenses. And for example, we can estimate them. For example, we can measure the mass function of isolated black holes, which I think is impossible to do otherwise. So our recent results show that the mass function of black holes is basically flat in the logarithm of mass, and also there is no large gap between black holes and neutron stars. All of these results are based on observations of the galactic center. However, we expect that there should exist quite a large population of microlensing events outside the galactic center, in the galactic plane. And here I'm showing just the expected event rate based on some galactic model. So we expect to find many microlensing events outside the galactic center. However, finding these objects was very difficult previously, because you have to observe huge areas of the sky. You have to observe the entire galactic plane at a relatively high cadence. And previous telescopes didn't have enough capabilities to carry out such searches. So this has changed with ZTF. ZTF, thanks to its huge camera, huge field of view of 47 square degrees, is capable of observing the entire plane with a relatively high cadence of 2 to 3 days. So this is like ideal data set to try to search for gravitational microlensing events. Of course, it's quite a difficult task because ETF is observing, I think, over 1 billion sources there. So finding rare microlensing events among 1 billion light years is extremely challenging task. So we used for that machine learning. We used neural network classifiers to search for microlensing events in our photometric data. Basically, for every light curve, we have calculated a set of features that describe that light curve. For example, the amplitude of the brightening, its duration, the quality of the microlensing fit to the light curve, and so on. And we trained our classifiers based on OGLE data. OGLE is, I think, one of the longest running microlensing surveys. They have huge databases, so we trained our classifiers based on real data from OGLE. And actually, we created two classifiers, one for single lensing events and the other for binary lensing events. Binary lensing events, that is, events caused by planetary systems or by binary star systems. And actually, it turned out that the performance of these classifiers was excellent. So we were able to correctly recognize about 90–80% of all single lensing events and about 80 to 85% of binary lens events, which is quite a good achievement. And here are some example light curves of those microlensing events. so far, my student Tony Rodriguez and I have found about 50 events in the galactic plane, and that sample is big enough to get some statistical information about the events in the galactic plane and how they are different from the galactic bulge. So on the left, you can see the distribution of our microlensing events in the sky in the galactic coordinates. So as you expect, all of these events are located in the galactic plane, and as we move away from the galactic center, the number of events is dropping. So this is actually what we expected to detect. On the right plot, you can see the distribution of timescales of events that we detected. So what is really exciting is that all of these events located in the galactic disk detected by ZTF, which are marked in black, have timescales that are a few times longer than events located in the galactic center. So actually, this was expected from theoretical models, but this is the first time that we could see it in the real data. So for the first time, these investigations are possible with ZTF, and I hope that after this workshop, you'll be able to find more exciting objects in our data. Thank you.